I am going to talk to you today on planetary science. This is a lecture which will give you an idea about the solar system bodies, which consist of planets, satellites, comets, asteroids and other minor bodies in our solar system. In the bottom of this first slide which you are seeing here is different planetary missions which India has undertaken. The first is the Chandrayaan-2 mission, then there is a Mars mission, and this is all possible because India now has the launch vehicle which can carry this kind of missions into space, and we can achieve the required velocities for getting inserted into an orbit around any planetary bodies. When we talk about the planetary science, I will give you an outlook on planetary science. You can see here different planetary bodies or planets in our solar system, and to give you a much better flavor about this, you can look at this slide which shows you the relative size of the planets and the sun. Looking at this, you can say that there are two classes of planets in the solar system: the inner planets, which consist of Mercury, Venus, Earth and Mars, and then there is the outer part of solar system which consists of big planets like Jupiter, Saturn, Uranus and Neptune. And now currently we do not consider Pluto to be a part of our solar system, and that is why the way to remember this order of the planets in our solar system is to say that my very excellent mother has just sent us 9 pizzas, that is Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune and Pluto. But since Pluto is now not considered as a planet, so we have only 8 planets in our solar system, and this rhyme changes to my very excellent mother just send us noodles. So, instead of 9 pizzas, it is just noodles. Now, when we talk about planetary science, we say that this is also known as planetology or planetary astronomy, which deals with the planets, planetary systems, the solar system and things like that. And essentially it covers a much wider gamut of scientific disciplines, which also includes earth sciences. Or we can say in some sense that planetary science is a parent and earth is a part of that planetary science system. Now, why we call or what we call or what we define a planet, or how do we define a planet? Planet is a celestial body which needs to fulfill 3 conditions. First, it has to go around the sun. Many of these bodies in the solar system, they actually go around the sun other than the natural satellites. The second one is that a planet should have sufficient mass for its self gravity to overcome the rigid body forces, which essentially means that a planet should be round in shape. And the third one is that a planet should have cleared its neighborhood. This third definition is not fulfilled by Pluto, because Pluto has a satellite which is called Charon, which is roughly half the size of the Pluto itself, and that is why Pluto is now considered as a dwarf planet or a minor planet. Now, in this slide you are able to see the relative sizes of these 4 terrestrial planets. We call them as terrestrial planets because they have surfaces very similar to our Earth. And if you look at this, you will say that Venus and Earth roughly are of same sizes. Mars is roughly half the size of the Earth or Venus. Mercury is about 1/3. But when you compare them with respect to the outer part in the solar system, you can say that Earth is very small. Roughly you can say 10 Earth can fit into the size of Jupiter. And so, Jupiter is the biggest planet in our solar system, second is Saturn, and then you have Uranus and Neptune. So, this outer part of solar system, which consists of these 4 big planets, they are also called as giant planets, because they are much bigger in size compared to the 4 terrestrial planets which I just mentioned. If you want to compare this with the sun, this is how it looks like. And now you can see, when we compare Earth with respect to sun, it looks like a dot, and almost like 100 Earth can fit inside the sun itself. And on this, now you compare yourself, where do you stand? So, this is the sizes of the planets in our solar system related to the sun. We now called our solar system as a new solar system, essentially because Pluto is now considered as a dwarf planet, and there are many other planets which have been discovered beyond the orbit of Pluto, which falls in the category of Kuiper belt objects, which includes Huma, Makemake, Eris, and things like that. We also have asteroids which also go around the sun, but they are also considered under minor planets. Ceres is one of those, which is the biggest. And then we have comets, and I will be talking about that in a moment. So, if you look at many other trans-Neptunian objects or Kuiper belt objects, in addition to Pluto, and now you can see the size of the Charon and Pluto, there are many of them like Eris, Makemake, Huma, Sedan, Acres, Quair, and Varna. Looking at the asteroid belt, which I just mentioned, which lies between the orbit of Mars and Jupiter, it is considered as if that a planet was trying to get formed on these orbits from the sun, but it could not, and hence there is a belt which is essentially filling this region, which we call as asteroid belt. The biggest of these asteroids is called Ceres, and it is almost 1000 kilometer in diameter, and it contains almost 1/3 of the total mass of this asteroid belt. These asteroids, Ceres of course looks like somewhat circular, but still it is not perfectly circular, but one can have asteroids of varying dimensions, shapes. For example, Ida and this asteroid also can have their own satellites. For example, here you see Ida having a satellite called Dactyl, which is Ida itself is, you can say, a body of about 30 or 40 kilometer in size, but it has its own satellite which is about 1 kilometer in diameter. They can have many varying shapes, you can see over here, and this is actually a photograph of Eros, which is also second largest near Earth asteroids. Why we are worried about near Earth asteroid is that these asteroids actually come much closer to the Earth, and if due to some gravitational perturbations they come into line of sight of Earth or basically head on collision with the Earth, then they can cause catastrophe on the Earth. Now, coming to comets, comets are very interesting objects in our solar system, whose sizes are very small, you can say about 1 kilometer to tens of kilometer only. And but when they come close to the sun, they start evolving into a huge coma and a long tail, which can be millions of kilometers long. So, comet is actually full of volatiles, and these volatiles start subliminating as they come close to the sun, and the heat from the sun give rise to sublimation of these volatiles. What you are seeing here is a picture of a comet Hale-Bopp, which had a appearance or visit into a solar system in last century end, and it is one of the brightest comet of that century, because it was very visible with the naked eye. Comets are also very interesting because they are believed to have brought water on the planet Earth and probably the life on the Earth. But if a comet strikes the planet Earth, they can cause catastrophe and devastation. So, it can be a life taker or a life giver. The size of the comet can be huge, and here you can see the size of a comet Holmes and its coma compared with the size of the sun. You can see both looks to be almost of the same size. What it essentially means that the coma or the atmosphere of a comet can be in very large dimensions. Now, here I am going to run through to you to tell about the dimensions in our cosmos, starting with dimensions in our neighborhood, where you can see a small garden, a road in between, and a bench on which a lady is sitting. If I zoom this picture by a factor of 100, this is what you look. Now, you can see the size of a small town or a city, and you can see the roads, you can see some flyovers. If you zoom this further, you go to the dimension of roughly an estate, and you can see in the middle of this red patches a black lines, which is nothing but a river flowing through across. If I zoom this further, you come to the dimension of the earth. So, essentially from a picture where I can see my neighborhood, if I take 3 steps of 100. So, now with this 3 steps, I am able to come to the dimension of the earth. If I take next step, I come to the dimension of earth moon distances. Essentially, that by 4 steps from my neighborhood, I am coming to the dimensions of earth moon system. And if I take one more step, I actually come to the dimensions of sun earth system. That means almost like 1 AU. As you can see here, now the number is very large. One can read it as 16000000, which can be converted into a much better unit, which you call as 1 astronomical unit. So, I can say that the distance between sun and earth, the mean distance is about 1 AU. Now, what happens if I take one more step of 100? I cross the whole solar system, and now I am even beyond the orbit of Pluto. So, that means by taking 5 steps from that neighborhood, I am crossing my solar system. What happens next? If I go beyond, I see my star, that is the sun, and nothing around it. That means there is no star in the vicinity of the earth within 11,000 AU. What happens next? If I take one more step of 100, now I can see many stars in the vicinity of our own star, that is the sun, within dimension of 1100,000 AU. Now, this is also a big number. So, I convert into a still bigger unit, which is called light year, and it becomes almost like 17 light years is equivalent to 1100,000 astronomical unit. If I take one more step, then I see much more stars, and with one more step, I am actually crossing the dimension of the galaxy, which is our own galaxy, the Milky Way. And our solar system is actually situated on one of the arms of this Milky Way galaxy. So, we have reached to the dimension of the Milky Way. What happens next? Let us see. If I zoom it further by factor of 100, I see the Milky Way galaxy, and I see a few other galaxies in the vicinity of Milky Way galaxies. And by zooming one more, I am going to a dimensions where I see many more galaxies. So, what I have done so far is essentially tries to convey to you the sizes with which we work when we are talking about the objects in our vicinity, to the size of the earth, to different solar system bodies, to the solar system, to the galaxies, and to the whole universe. So, if I summarize this, I have taken only 12 steps to come from my neighborhood to cross to dimensions of the universe. But you must have noticed that I am not showing anything beyond that, and the reason for that is, if I take one more step, I will be actually crossing the dimensions of the universe, and what we know now is that it is only 14 billion years. Now, let us come back to our solar system, and this is what I have just showed to you in one of the slides. So, we will come back again from this to our earth, and this is how the earth looks like. And if you look at the tilt of the earth, which is about 23.5 degrees, which essentially means that earth is not vertical as it goes around the sun, it is actually tilted like this. Now, this tilt is is important because this provides seasons on the planet Earth. And if you want to look at the tilt of the other planets, this is how it looks like. The tilt of Earth, Mars, and you can say Saturn are somewhat close by, about 25 degrees. But if you go to a planet like Jupiter, it is almost vertical. And if you go to a planet like Venus, it is almost 180 degree, which in turn means that it is not moving in the way all the planets are moving, it is moving in retrograde. And if you go to a planet like Uranus, it is pole on. So, this weird planet Uranus actually rotates like this rather than rotating like this. And you can also see similar situation for Pluto. So, that means we have planets in our solar system which have very large differences in terms of its rotation axis. Let us look what happens for the masses. Of course, Jupiter is the biggest planet in the solar system, and hence it is the most massive. The second massive is Saturn, and then comes Uranus and Neptune, and Earth is coming at the 5th position. But if you compare them in terms of their length of the day, that means how much time it takes to complete one rotation on its axis, which is length of the day, you can see that is not Jupiter, but Venus which is topping. It takes about 243 Earth days to complete Venus to rotate on its axis. That means it will have about 120 days day and 120 days night. Similar is the situation for Mercury, which takes about close to 50 or 60 days to rotate on its axis. And if you go to Jupiter, you will find that it has a rotation period even less than 1 day. It is exactly about 10 hours, which in turn means a huge planet like Jupiter is spinning on its axis, completing its rotation in 10 hours. That means 5 hours day, 5 hours night. On Jupiter, 120 hours day, 120 hours night, 120 days day and 120 days night on a planet like Venus. If you look at densities of the planet, which is plotted in this, here the planet Earth tops, and you can see the density of the planet Earth is highest, it is close to 5.5 gram per cc, and here Saturn is the lightest, whose density is less than 1, which in turn means that the planet Saturn can actually float on water. Let us look at the magnetic field configuration of the planets, which is shown over here. And in our solar system, we have only 5 planets which have intrinsic magnetic field: Earth, Jupiter, Saturn, Uranus and Neptune. And if you look at the tilt of this magnetic axis with respect to the rotation axis, you can see that the planet Earth and Jupiter has somewhat similar tilt. Saturn is perfectly aligned, but Uranus and Neptune has much larger tilt between their rotation axis and the spin axis, which in turn means their magnetosphere configuration will be very, very different compared to the planet Earth itself. Now, once the planet has magnetic field and it has an atmosphere, it will be having a huge magnetosphere which looks something like this, where a normal magnetic configuration which you see over here down converts into this kind of configuration because of the plasma coming from the sun, which is called as a solar wind. So, you have a cocoon shape which actually shields the planet Earth from this harmful radiations, or essentially you can say the charged particle radiation coming from the sun, and this helps us to deflect this high energy charged particles across the boundaries and does not allow them to enter into the Earth's atmosphere. This can also cause auroras, which you see over here, and these auroras can be in different colors, which you see over here. It can be bright red, it can be greenish, yellowish or even bluish. And this aurora is a phenomena of the interaction of the solar wind, which is a wind of plasma coming from the sun interacting with the upper atmosphere of a planet. This phenomena is common to all the planets in the solar system which has a magnetic field and an atmosphere. So, one can see also aurora on Jupiter, which is shown over here. This is the north pole, this is the south pole, and you can see the aurora on Jupiter, as well as on Saturn, where you see this is the north pole and this is the south pole. So, aurora is a common feature of the planets which has an atmosphere and magnetic field. Now, this aurora which I am showing over here in the ultraviolet or far ultraviolet, it can be seen at many other wavelengths. For example, here I am showing the aurora on Jupiter in X-rays, in the visible or in the infrared. And all of this is actually caused by different processes of the interaction of the charged particles with the atmosphere at different heights. Now, let us look at the composition of different planets in the solar system. So, here you see the relative composition of the planet Venus, Mars and Earth, where one can say that Venus and Mars are dominated by carbon dioxide CO2, and N2, which is the dominant gas on Earth, almost like 80%, is a very rare commodity on Mars and Venus. It is just few percent. But on the Earth, we have a huge abundance of oxygen, close to 20%, which is not present on the planet Mars and Venus. Now, if I look at the other planets in the solar system, I can actually tabulate them in this table, and I can say that there are many classes of atmospheres in our solar system. The first one which is there is the outer planets, which we call as giant planets, and which is dominated by hydrogen and helium. So, Jupiter, Saturn, Uranus and Neptune have a much similar configuration of composition dominated by hydrogen and helium, but they do have a significant amount of methane and ammonia. The second one is of course, the terrestrial planets Venus and Mars dominated by CO2, but the second dominant gas is N2. Then we have N2 dominant atmospheres like Titan, Earth, Pluto and Triton. Titan is actually a satellite of Saturn, which is the second largest satellite in the solar system, and it has an atmosphere dominated by nitrogen similar to that of Earth, Pluto and Triton. And Triton is actually a satellite of Neptune, which is the largest satellite of Neptune. So, one can see that Earth, Pluto and the two satellites are actually dominated by nitrogen, and it is quite intriguing to know that this N2 dominated atmospheres of the satellites are around atmospheres which is dominated by hydrogen and helium. If you go to other objects in the solar system, you can say Io, which is a satellite of Jupiter, the most volcanically active body. It has an atmosphere dominated by CO2, and then you can say Moon and Mercury, which does not have a significant atmosphere, but they have much lower densities in the atmosphere, which we call as exosphere. And then we have comets, which are essentially watery bodies, and therefore H2O is the dominant atmospheric composition. But in addition to this, they have CO2, CO, methane and all host of many other species. Now, any planet which has an atmosphere is bound to have an ionosphere. It is essentially because of the solar radiation which comes from the sun, which interacts with the atmosphere, causes these particles to get ionized, and we get the formation of the ionosphere. So, now if I compare these planetary bodies with their atmospheric composition, which I just talked about, I can see here that all of them have ionosphere, whose abundances in terms of density is shown over here, and essentially you can say that it decreases, or the density of the ionosphere decreases as you move away from the sun. But the more important point is that whether the dominant gas actually constitutes the dominant atmospheric ionospheric species. For example, if you look at Earth, we have N2 as the dominant atmospheric gas, but the dominant ion is not N2 plus, it is an O2 plus. Similarly, if you go to Titan, which is again dominated by nitrogen N2, and methane is the second most abundant gas, but it is still just on a few percent. the dominant ion is HCNH plus, or you can say H2CN plus, which is none of these ions. So, essentially photochemistry is playing a dominant role in the atmosphere, which converts these major ions into some different ions, and which becomes actually the dominant ionospheric composition. Similarly, if you go to Venus and Mars, where you have CO2 dominant atmosphere, but their dominant ionospheric species is O2 plus, not CO2, not CO, not N2 and not O also. So, one has to actually understand of what is happening in the atmosphere to know about the processes as well as the dominant ionospheric species. I mentioned about EO, and I also mentioned that this is the most volcanically active body in a solar system. It almost looks like a pizza, because it has lot of CO2 pumped out, almost like 1 ton meter per second, which comes into the atmosphere and then falls back on the surface, causing huge change of sulfur, and this coloration which you are seeing over here is coming out because of chain of the sulfur. If you compare this with other Galilean satellites, so this is Io, and then we have Europa, Ganymede and Callisto. These 4 are actually called Galilean satellites because they were discovered by Galileo Galilei in 1600 using his primitive telescope. Ganymede is actually the biggest satellite in our solar system, and it is even bigger than Mercury and Pluto. So, here you can see much better comparing Ganymede with Mercury and Pluto. You can say even Titan is bigger than Mercury, and Titan is actually the satellite of Saturn, whereas Ganymede, Io, Callisto and Europa are the satellites of Jupiter. Moon comes at the 5th place in terms of the sizes of the satellites in our solar system. And Moon is very interesting because this is the only natural satellite of the planet Earth, and you must be aware that India has sent its mission to Moon called Chandrayaan-1, which was launched on 22nd of October 2008. So, we have almost completed 1 decade of this mission. It reached the Moon on 8th of November, about 16 days later, and it had 11 experiments on board, which is shown over here and listed over here. And this mission was truly international character with almost like 10 countries participating in this mission. On this mission, we had an experiment which is called SARA, which stands for Sub-keV Atom Reflecting Analyzer. And this SARA essentially consisted of 2 sensors, SENA, which stands for Chandrayaan Energetic Neutral Analyzer, and then SWIM, which stands for Solar Wind Monitor. And the idea behind that was to actually understand the interaction of the solar radiation and you can say the solar wind with the surface of the Moon. Chandrayaan-1 has given a lot of interesting science results, including the discovery of water on the Moon. Before Chandrayaan-1, we all thought that Moon is bone dry, there is no water on the Moon, but Chandrayaan-1 mission has told us that no, water is present on the Moon, not only the surface, but also in the atmosphere in form of water molecules. In addition to this, it has informed us about the validation of the magma hypothesis, discovery of mini magnetosphere on the Moon, talking about very recent volcanic activities as old as 100 million years, and we have also found couple of rallies which are essentially undamaged lava tubes, which can actually be used for human habitat once the human landing starts as a continuous program on the surface of the Moon. Many results have come out from this Chandrayaan-1 mission, which are reported in more than 150 publications, and some of them have actually formed the cover pages of scientific journals. And one of the images which has come out from the Chandrayaan-1, which I like very much, is this one, where one can see the Earth rise on the surface of the Moon. And this image was taken on 22nd of July 2009, when we had the solar eclipse. The idea here was to actually look at the shadow of the moon falling on the earth, but unfortunately it was very cloudy, as you can see over here, and that is why we are not able to see very precisely the shadow of the moon on the earth. But still one can very clearly see the surface of the moon and the earth rise over the moon surface. Now you can actually see how the surface of the moon looks like. The moon is actually full of lot of undulations or morphological changes, topographical changes, and it is full of craters. So, all the spots which you are seeing on the surface of the moon is nothing but craters, and these craters have varied dimensions starting from centimeter size to kilometers to hundreds of kilometers to even thousands of kilometers. You can see the differences in the albedo. Some portion looks dark, some portion looks bright. There are subtle differences in the mineralogical composition, the morphological changes, and things like that. Now, how does this kind of surface have an interaction with the solar wind? So, I showed you this in terms of how the interaction looks for the planet Earth, which has an atmosphere and a magnetic field, but a planet like Mars or Venus, which does not have an atmosphere and magnetic field, the interaction forms a cavity like this, very similar to the Earth, but the solar wind dynamic pressure is essentially balanced by the ionospheric pressure, and we get an ionopause which deflects the solar wind. But now, in the case of moon, which does not have an atmosphere and magnetic field, the interaction is very different. Whole solar wind was assumed to come and hit the lunar surface and get absorbed, and on the night side you have a plasma wake or a vacuum. Now, you assume that moon is going around the earth. So, earth is here, this is the orbit of the moon which is going around the earth, and this is the magnetosphere and this is the magnetotail of the earth, which I just mentioned about. So, if you look at this geometry, you will say that moon is outside the earth bow shock and magnetosphere almost like 2/3 of its orbit, and about 1/3 of its orbit it is inside the earth sphere of influence in terms of plasma, and that is why the plasma which is going to hit on the lunar surface will be very different here compared to the unperturbed solar wind in this part of its orbit. What we knew about the interaction of the solar wind with the earth is that the solar wind, which is basically protons, 95% of them and few percent doubly ionized helium, comes and hits the surface, get absorbed, and we get a vacuum or a plasma wake cavity over here, which gets filled up at the speed of ionocaustic velocities, and this filling actually takes very long downstream, almost like few lunar radii, which translates into something like few thousands of kilometers to tens of thousands of kilometers. We also knew that there are surface magnetic anomalies or local magnetizations whose strength is very small, of just about 100 nanoteslas, and that it is full of regolith and dust, which can be seen in imprints of human landings. This simple geometry of the interaction has changed drastically with the Chandrayaan-1 mission, and in particular with the SARA experiment on the Chandrayaan-1 mission. Now, we know that this geometry is looking like this, where you can see many arrows, and each of these arrows is actually a scientific publication. There are many processes which is happening, including that it is not a complete absorption of the solar wind plasma on the lunar surface, but a significant part is actually backscattered from the lunar surface, and that could be protons converted onto neutral hydrogen and coming out. It is almost like 20%. We have sputtered oxygen which is coming out on the surface, almost like 4 to 8%, and we have protons coming out as protons, or you can say backscattered as protons, but the percentage is just 0.1 to 1%. We also discovered mini magnetosphere on the moon's surface, which in turn means that the small magnetic anomalies on the lunar surface of few hundreds of nanoteslas can actually stop this impacting solar wind and deflect these charged particles through a potential which is developed around the mini magnetospheres. So, our understanding about how the moon was interacting with the solar wind has completely transformed and changed with the Chandrayaan-1 mission. Now, I will talk little bit about the Mars orbiter mission. And this is the first interplanetary mission of India, and as you must be aware that India is the first country in the world to have the successful insertion of an orbiter around the Mars in its first attempt. Mars orbiter mission, or the MOM, has completed 4 years in its orbit around Mars, and it is going very strong. It was launched on 5th of November 2013 and arrived at Mars on September 24th, 2014 after a 10 months journey. There are 5 experiments on the Mars orbiter mission, which we will call as payload, which has a mass of about 13 kgs. And one of the experiment on which I was directly involved is called MENCA, which stands for Mars Exospheric Neutral Combustion Analyzer. And this experiment was essentially meant to measure the atmospheric composition of the Martian atmosphere. This shows the accommodation of these payloads or the experiments on the MOM mission, and you can see here that all these imaging payloads are mounted on one side of the spacecraft because they are all meant to look towards the Mars, but MENCA is mounted along the roll axis. This is the roll axis of the spacecraft, and the point here is that MENCA is actually looking at the in situ measurement of the atmospheric constituents, and therefore, it has to be along the velocity vector which is along the roll axis. This experiment has produced very exciting results, and one of them is about the evening time exosphere of Mars. Essentially what it means is that we are looking at the Martian atmosphere higher up at altitudes of about 250 to 300 to 400 kilometer at the evening time. You can see here this is the Mars, this is the day side, this is the night side. The orbit of the MOM is such that it enters the Mars or becomes closer to Mars on the dawn side or the morning hours and comes out in the evening hours. And this is the time when it is closest to the Mars, and we are able to see this evening hours atmosphere and how does it vary. Now, as you must be remembering that I was telling, CO2 is actually a dominant gas in the Martian atmosphere, but you go up somewhere around 265 to 300 to 400 kilometer, you found it is atomic oxygen which is a dominant gas, not CO2. CO2, if you see over here, has a densities of just somewhere around about 10 to the 6 to 10 to the 7, whereas O has a density still higher because it is all red over here. Essentially meaning that O takes over as a dominant gas when you go up in the atmosphere. This is another publication which has come out from the MENCA experiment on the Mars orbiter mission, which is a discovery about the suprathermal argon. Suprathermal means they have what you called temperatures which is larger than the normal temperature expected for any atmospheric constituent. And if you look at this cartoon, it shows us that where we are talking about, this is a what you call scale which talks about that height at which we are talking about. This is about 100 kilometer, this is 200 kilometer, this is 300, 400, 500. This is the MOM orbit around Mars at its closest approach, and at this kind of orbits we have seen that there are 2 different temperature profiles or 2 different density profiles for argon, which in turn means that argon has a much higher temperature when we are seeing this kind of density profile because the gradient is different, and this difference is very subtle and it translates to almost like more than 100 kelvins, essentially meaning that you have suprathermal argon present in the exosphere of Mars, which has a temperature about 100 to 150 Kelvin higher than the normal argons. And this is a discovery because this has now changed our understanding in terms of why argon, and not only argon, we have also seen CO2 having a higher temperature than the other species. So, we are looking into this issue in terms of understanding of what is the processes which is causing this differences, and this has implications because if you have a temperature which is higher, this will aid in escaping of these atmospheric constituents from the Mars. The next mission which is in planning for India is the Chandrayaan-2 mission. You must have heard about that. This is a very complex and complicated mission, because in addition to the orbiter which was there on the Chandrayaan-1 mission, it also has a lander and a rover, and this is how it looks like. So, you have an orbiter, you have a lander which we now call as Vikram lander, in the memory and tribute to Professor Vikram Sarabhai, the father of the Indian space program. And we have a rover, and this rover will actually come out from the lander. You can see over here, this is the place from which this what you called ramp will open up, and the lander will roll out and move on to lunar surface. And we are planning this mission for having a landing somewhere in the higher latitudes of the moon, or you can say close to the polar regions. And this will be the first time that we will be actually probing the moon at higher latitudes of the polar regions, because no other landing has so far taken place in the polar regions. And this is a very important mission, because we have experiments on the orbiter, we have experiments on the lander, and we have experiments on the rover. So, we are going to have observations from the orbiter when the lander and rover are also working, and that will be a unique combination of getting the science from the moon very close to the surface and from almost like 100 kilometers above the surface. So, there is very exciting time ahead in terms of planetary exploration for India. We are also working on many other missions which are under planning, and which I will be able to talk to you later in the time. So, thank you all for listening.